So in lecture B, we're going to now look at applications to areas beyond math, applications to probability, finance, and physics. You might say probability is just math, isn't it? Well, I think probability is one of the most useful areas of math. I hope you know that by now. So I'm going to think of it in a real world context, actually. Finance and physics are certainly related to the real world. As an example of an application of probability, I'm going to consider the situation where you are rolling one die, six-sided die. Die is the singular, by the way, for dice. Okay, so don't say one dice, say one die. So you've got one die in your hand, you vigorously roll it down the floor. What does it come up? Does it come up 1, 2, 3, 4, 5, or 6? Each side of the die has equal probability of 1/6 of coming up. You might want to know the question of, before you start rolling, how long will it take me until I get my first 6? Now, since each side has a probability of 1/6, you might guess that the most likely answer is it might take you 6 times until you get a 1/6. Though you know, of course, you could get it on the first roll, or the second roll, or the third roll. Or it could take a long time. It could take 20 or 15 or 15, I meant to say 10, 15, or even 20 rolls, so that seems unlikely. If x is the number of rolls until the first 6 of a fair die meaning each side has a probability of 1/6 of occurring, then x is said to have what's called a geometric distribution. It's an example of a geometric random variable. It's a discrete variable instead of continuous. Every probability variable we've thought about so far has been continuous, because that's what calculus sort of most applies to, is continuous situations. But infinite series can apply to discrete situations, this being one of them. You could ask, what is the probability that x equals 1, for example? What's your chances of getting a 6 on the first roll? Well, I hope it's intuitive that that should be 1/6. Since you got a 1/6 chance of getting a 6 on any one roll, the chance of it taking one roll until you see your first 6 would be 1/6. X is discrete. It can't equal 1.5 or 1.76. The next value it could be is 2. What is the probability that x equals 2? Well, that means it took 2 rolls until you saw a 6. Your probability, that means you did not get a 6 on the first roll, but you did get a 6 on the second roll. Your probability of not getting a 6 on the first roll is 5/6. And your probability of getting a 6 on the second roll, assuming there is a second roll, is 1/6. It does turn out, and I hope it's somewhat intuitive, that that product is the answer. It's a long probability that, in this case, to find the probability that you did not get a 6 on the first roll, but you did get a 6 on the second roll, you figure out the probability of not getting a 6 on the first roll, which is 5/6, times the probability of getting a 6 on the second roll, which is 1/6. And these rolls are independent. You just, each time you roll, you grab the die, you sort of shake it up in your hand, don't look at it, and vigorously throw it down again. It turns out you can multiply these probabilities. It's the same as 5/6 squared or 5/36. What's the probability that it takes you 3 rolls to see your first 6? Well, that means you did not get a 6 on the first roll, which happened with probability 5/6. You will not get a 6 on your second roll, which will happen with probability 5/6. But you do get a 6 on your third roll, which happens with probability 1/6. So this is 5 squared over 6 cubed, 25 over 216. See a pattern here? 1, by the way, is 5 to the 0. The probability of getting a 6 on your for the first time On your fourth row would be 5 6 times 5 6 times 5 6 times 1 6. 5 cubed over 6 to the fourth. 5 cubed is 125. I'm not sure what 6 to the fourth is offhand. 1200 something. 1296, yeah, okay. Etc. That's the pattern. Now, what do we know about probability distributions? For continuous variables, you got a PDF, probability density function, its integral has to equal 1. There is no PDF here in that sense, in the same sense, but there's, in a somewhat similar sense, a PDF. Essentially, these are the values of the PDF for this function, and instead of integrating to 1, they have to add to 1. So this is more of an application of geometric series more so than Taylor series in particular. But the sum has to go on forever, because theoretically it could take you 20 or 100 or 1,000 or 1,000,000 times to get your first 6. That's not likely, but it's theoretically possible. All those probabilities that go on forever must add to 1. And this is a geometric series with first term A equals 1/6, and common ratio R is 5/6. It will sum to A over 1 minus R. 1/6 divided by 1 minus 5/6. 1/6 divided by 1/6 is 1. So I use geometric series there, not really Taylor series, but although you can think of Taylor series, some Taylor series are geometric, so it could be thought of that way. Okay, so it's an application of geometric series, infinite series. And you can use this model to simulate rolling dice, for example, and counting how many times it takes you to see your first 6. If that was of interest to you. Fairly simple situation. What's an application to finance? Here it is. Present values of what are called perpetuities. Isn't that a great word? Perpetuities. What are perpetuities? They are annuities with no end. They go on forever. Those annuities could be paid continuously, and you'd have to find the present value with an integral, or they could be paid discretely, say once a year. You might wonder, what is the present value of a perpetuity, an annuity that goes on forever, that pays you $1,000 starting right now, say, and every year for the rest of your life, as long as you live, and every year after that to your descendants for as long as they live. Okay, for some reason you've gotten some sort of great deal like this. What's the present value of that? Is it finite? Is it a finite present value? It turns out it typically is. You do need to assume a constant interest rate, say of 5%, that's what we were typically doing before. Of course, in reality, that's not something that typically happens in real life, although it could happen on average over time. Remember, with present values, you have to sort of yank these values back in time. The present value of the first payment is $1,000, because that payment is happening right now. The present value of the second payment is 1,000 times what? You have to pull it back in time, not push it forward in time, so you have to divide by 1.05, not multiply times 1.05. When you divide by 1.05, that's the same as multiplying by 1.05 to the negative 1 power. This is also really an application of geometric series, not just Taylor series. The third $1,000 payment is 2 years in the future. You've got to pull it back 2 years. You need to multiply by 1.05 to the negative 2 power, etc. This is a geometric series, and it goes on forever because you've got a perpetuity. That's going to pay you forever. Your present value is not going to be infinite. This will converge because, okay, well, that's not the same as the common ratio. That's the interest rate. Maybe I should call this interest rate. 5% per year, compounded once a year. The common ratio here is going to be 1.05 to the negative 1. 1 divided by 1.05. Not the same as the interest rate, but it's, of course, related to it. A is 1,000. This is going to converge to 1,000 over 1 minus 1 over 1.05, whatever that happens to be. 1,000 over 1 minus 1.05 to the negative 1. $21,000. So in effect, even though you're getting $1,000 at the end every year, starting now, forever, to you and your descendants, of course the rule can't go on forever. It has to stop sometime. Its present value for those infinitely many payments is finite, $21,000. So if you were getting a 5% rate of return, you'd only need $21,000 in the bank or in your investment that returns 5% to be able to be paid forever like this. You are getting paid, but you're also earning interest at the same time. And it's enough to make this last forever. Imagine what's going to happen with your balance here. Pretend you've got $21,000 in some account that is earning 5% interest. You take out 1,000 right away, it goes down to 20,000, but then it grows by 5% the next year. 5% of 20,000 is 1,000. It grows to back to 21,000. Then you take out another 1,000. That's why it goes up forever. The balance just keeps oscillating between 20,000 and 21,000. All right, we'll finish today with physics applications, and in particular something called relativity. I guess you can even call it special relativity. Einstein. There's something called special relativity, and then there's general relativity. Einstein is the founder of both subjects, though of course there are other people that are important too. Einstein wrote his paper about special relativity around 1905, I think is what they say. He was a patent clerk at that time. He wasn't working as a university professor. But it made him famous, and then he got university jobs. About 10 years later, 1915 or so, he came up with the theory of general relativity. They're both strange subjects. Special relativity is a lot easier than general relativity, though. General relativity is pretty nasty as far as the level of math goes. Special relativity, though, you can do with just algebra and calculus. What we're going to do in discussing special relativity is not talk about the subject of relativity in general, but just trust that some equations we're going to look at are needed for special relativity. If you've got your book, it'd be good to open to page 558. I think what I'll do here is I will go over a couple problems that I'm also going to assign. So essentially the rest of class here, last 20 minutes or so, I'm going to assign the two problems that I'm going to talk about here. I'm not going to do them completely, but we'll do them partially. Let's see how Taylor series are being used. And this really will be Taylor series rather than geometric series. First problem is to look at number 40.
Wait, which page again?
558.
558.
I didn't have time to type out these problems, so I'll say them verbally to you. One of Einstein's most amazing predictions was that light, traveling from distant stars, should bend around the sun on the way to Earth. People thought that would be a strange thing if that happened, so that would be a surprising prediction to make. His calculations involve solving for phi in a certain equation involving trig functions. We're not explaining where this equation comes from, we're just trusting that he had to do this. solving for phi in an equation like this. Pretty complicated equation where b is this very small positive constant. B positive and small, whatever that means. In part A, you're supposed to explain why the equation should have a solution for phi, which is near 0. And in part B, you are to express the left-hand side of the equation in the Taylor series about phi equals 0, disregarding terms of order phi squared or higher, and then solve for phi. Well, probably the easiest approach to part A is to actually use the 0th degree Taylor polynomial for the cosine, say, and maybe not the sine, just leave the sign there, and argue why you can solve the resulting equation. When phi is small, by small I mean close to 0, the 0th order Taylor polynomial for the cosine is just a constant function 1. Cosine of a small angle, a small number, is very close to 1. You can try it in your calculator. Cosine of 0.1, for example, is very close to 1. Cosine of negative 0.1 is very close to 1. And if cosine is close to 1, then cos squared should also be close to 1. And its Taylor polynomial would start with a 1 as well. You could think about multiplying the Taylor polynomial for Taylor series for cosine times itself, and they both have a 1 at the beginning. Your first term would be 1 for cos squared as well. So, the equation above can be replaced. How should I phrase this? I don't know the best way to phrase this. Maybe replaced approximately. We are being kind of vague here. By sine phi plus b times 3. Replace the cos theta and the cos squared theta with a 3. Which is equivalent to sine phi equals negative 3b. And if b is small, close to 0, it is positive. Negative 3b is also going to be close to 0, though negative. It will be small too, in the sense of being close to 0. And yeah, you can solve such an equation for the angle. You can take the arcsine of a number that's close to 0. You can't take the arcsine of a number bigger than 1 or less than negative 1. But we're sort of implicitly assuming that if b is small, close to 0, then negative 3b is close to 0 as well. We don't know what b is exactly, but by the phrasing, the implicit assumption is b is so small, so close to 0, that negative 3b would be also very close to 0, and you can take the arcsine of both sides to solve for b. Arcsine of 3b, negative 3b, excuse me. And the idea then is this equation should have an answer, a solution that's not too far from that. Will it be exactly arcsine of negative 3b? No. But it shouldn't be too far away, is the idea. Okay, so that's essentially the justification I would give for A. Part B says, essentially we did part B as well. There's not too much to do this one, actually. Expand the left side of the equation about phi equals 0, disregarding terms of order phi squared. I guess we're supposed to replace sine with an approximation for it as well in part B, though. So there's going to be something new to do here. In part B, sine of phi is approximately phi. You could also say it's approximately phi minus phi cubed over 3 factorial, phi cubed over 6. But they're saying to ignore terms of degree 2 and higher. With the cosine ones, we still would use 1 here. We would not bother putting minus phi squared over 2 factorial, and whatever it would be for this one. So essentially your equation becomes a new approximate equation, which is very easy to solve for phi. So I guess I basically did that problem for you, though I didn't write everything that you should write.
So how did you get that sine of phi is almost equal to phi?
Based on the Taylor series, the Taylor series for sine of phi would be phi minus phi cubed over 3 factorial plus phi to the 5th over 5 factorial, etc. When phi is close to 0, I can get good approximations by ignoring every term but the first one. That's what I did.
Okay, so we already know that phi is close to 0.
Yeah. I think that's why they had to do part A. And in fact, yeah, I mean, the arc sine of negative 3b would also be close to 0. Because it's close to 0 and the arc sine of 0 is 0. So there's some extra words you should put in here when you do it, based on things I've said there. Emphasizing that b is close to 0, so negative 3b is close to 0. Arc sine of 0 is 0, and so the arc sine of this should be close to 0. That sort of justifies this second step in part B. The answer for phi should be close to 0. Second problem involving relativity is number 44. You know, people, I think a lot of physicists believe the mathematical calculations that Einstein did and the logic he used back when he first published his main paper in 1905. I don't know if they were completely convinced that reality followed relativity, but I think it was either light going, bending as it went around the sun, or something in the orbit of Mercury that finally convinced people that relativity actually was a good model for reality. There were predictions about what they would see, and it matched predictions. Okay? So that equation that we were just looking at might have been a historically important kind of thing for verifying that relativity was a good model of reality. Number 44, we've got this equation, m equals m0, or m naught if you prefer, divided by square root of 1 minus v squared over c squared. This is an equation that gives you something called the relativistic mass, m, of an object moving at speed v, where c is the speed of light, and m0 is the mass of the object when it is at rest. What in the world is going on there? Well, it turns out that when you move, your mass is different than when you stay still. Now, before Einstein came along, nobody believed that. But it's true. M is your relativistic mass. It's the mass you would weigh yourself, being if you were, let's say, okay, you're not walking and standing on a scale at the same time, but you're like in a spaceship, and okay, the spaceship has artificial gravity that's the same as the gravity of the Earth. And you stand on a scale in the spaceship that's moving very fast, it's going to weigh you to be what? To be heavier than you are on Earth. If v, in fact, is close to c, the speed of light, then v squared divided by c squared is going to be close to 1. 1 minus something close to 1 is close to 0. Square root of something close to 0 is close to 0. This fraction is going to be very big. In fact, will go to infinity as v approaches c. Your mass goes to infinity. Oh, no. As you approach the speed of light. And it's evidently been proved that that does happen. I'm not sure what kind of experiments you do to prove that. We haven't, accelerated anything but subatomic particles to near the speed of light. What's the goal of the problem, though? Use the formula for m to decide what values of v are possible, what values of v are in the domain of this, essentially. Hint, v can't be bigger than c. V can't even equal c. Sketch a rough graph of m as a function of v, labeling intercepts and asymptotes. Part C, write the first three non-zero terms of the Taylor series of m in terms of v. Part D, for what values of v do you expect the series to converge? I sort of think in problems like this you should maybe do parts B, C, and D kind of all at once. If you label it that way, this is part B, C, and D all at once. I think that's probably the best approach. I mean, yeah, you could pick some values for m0, and you can look up the value of c and graph this. But I would like to go ahead and find the Taylor series, and based on the Taylor series, figure out what the graph looks like even without technology. The key thing to do is to realize you can use the binomial series formula for this. You do not need to use the formula involving the derivatives of this function of v, which would be kind of nasty. You can write this function as m0 times, let me write it like this, 1 plus, in parentheses, negative v squared over c squared to the negative 1/2 power. That's the best way to write it. Why? Because that's reminding me now of this formula, that 1 plus x to the p is 1 plus p times x plus p times p minus 1 over 2 factorial times x squared, etc. The next term would be p times p minus 1 times p minus 2 over 3 factorial times x cubed. It's reminding me of that with p equal to negative 1/2, and replace the x with negative v squared over c squared. And the m0 just stays out in front, though at the end I can multiply it back through. That's the best way to get the Taylor series here. When v squared over c squared is close to 0, so v is relatively small compared to c. V is definitely less than c, I guess even v could be close to c, and this is still valid. Because this converges when the absolute value of the x is less than 1, and if v is less than c, that will happen. So again, use the formula. P is negative 1/2. X is negative v squared over c squared. Be careful with your signs, for example. One more term would be negative 1/2 times negative 3/2 times negative 5/2 over 3 factorial times negative v squared over c squared cubed. Yes, I am sort of doing part C for you here. If you want the first 3 non-zero terms, we could actually stop right there. Just for the sake of doing it, we'll do the first 4 non-zero ones. Now multiply the m0 through and simplify. You'll get an m0 in every term. Maybe it'd be better to leave the m0 out, but we can bring it in. Should I leave the fractions as v squared over c squared, or should I bring the c squared out in front? It really doesn't matter. I mean, I could do this and continue that way. What's the next one going to be? I'm going to get a plus, actually, for all of these, because here I got 2 minuses there and there making a plus. Here I've got 2 minuses there and there making a plus, and this negative is squared. Here I've got 3 minuses making a minus sign, but this negative quantity is cubed, so I get a 4th negative sign. Every term is going to involve a plus sign. To me, like the next one is going to be 3 over 8 times c to the 4th times v to the 4th. And then a plus, what will this one be? I'll get a 15, that's an 8, and another 6, 48, 15 48ths, which reduces to 5 16ths.
Don't you still need the initial mass? And the
Yeah, I do need to do that, thanks. You could write it like that. You could combine the c's and the v's. You could write this as, and even write it as v over c quantity squared if you prefer, right there. You could write this as v over c to the 4th. There are different ways to write these things that may or may not be useful. V over c to the 6th power there. You could do that kind of thing. Maybe you focus more on the ratio of v over c than the value of v itself. It's going to be valid as long as v is less than c in absolute value. Can you use this information to draw a graph? Of m as a function of v. Well, the m-intercept is going to be m0. When v is 0, your mass, your relativistic mass, is your actual mass, so to speak. The slope at 0 is evidently going to be 0 because there is no linear term here in v. But there's a quadratic term whose coefficient is this, which is positive. It's going to be concave up. And yeah, I mean, you could try plotting more points. It's going to look like this. It's going to end up having a vertical asymptote at v equals c. You can figure out what that graph looks like without the series. But I think it is good to have the series, and especially if you need polynomial approximations to this thing for some other purpose, it's good to have this series, and then just use as many terms as you might need in whatever you're doing, whatever situation you're trying to apply it to. That's the idea of what it really is useful for. Okay, have a good day.